Okay, so in this lecture, I want to move into the first carboxylic acid derivative, and that's going to be the acid chloride. Whoops, sorry, I'm in red here. Chemistry of acid halides, I will say generally, but mostly these are chlorides. Chlorides react well enough, and they're pretty easy to make. Fluorides are coming on the scene. They're actually becoming pretty useful, the acid fluorides. But for a while, there wasn't a great practical way to make them, so their chemistry isn't as developed. But they're actually fairly practical, whereas acid bromides and acid iodides, I would say, are a little too unstable to be practical. But you can kind of generate things like these if you need to. So before we get into specific reactions of acid chlorides, let's talk about the synthesis of acid halides. And so there's generally two synthetic routes. We don't need to worry about mechanism for these two. About these two. So let me present two, and then I'll show you a third one. We can worry about that mechanism, but not these first two. Okay, so in this first reaction, what you do is you take a carboxylic acid and you react it with SOCl2. There's actually a lone pair on this sulfur atom. In this depiction, it has an expanded octet. We could show a resonance depiction with charge separation, but everything has an octet. That might be better. But this is thionyl chloride. So thionyl chloride reacts to give this species. And again, just an acid chloride. And again, we'll say no mechanism here. We could then take a carboxylic acid and do similar chemistry with a new reagent. It's going to be PBr3, phosphorus tribromide, and this is a way to introduce the acid bromide system, but you have an unstable starting material with PBr3, and then you get a super unstable functional group as a product. Again, this is a no mechanism one, but these are reactions that appear on like MCATs and that sort of thing, so they're pretty useful to know. So Willoughby, though, that is I have a favorite. I'm going to make sure it's not coupled with that PBr3 reaction. But Willoughby's favorite is as follows. What you do is you take a carboxylic acid. So the general starting material for all of these things is a carboxylic acid. And we're going to mix that with oxalyl chloride and a common organic solvent. We use this a lot in the SN2 reaction section. This is called DMF. Now, what's cool about this is the DMF is actually a catalyst for the reaction, so you just need one drop of the DMF. And here's our oxalyl chloride. So it's going to be doing some interesting things where we are going towards product by releasing some volatile gases, and that gives us our acid chloride. So another way of making acid chlorides. But this is my favorite set of conditions I do this reaction whenever I need a carboxylic acid. It's just so reliable. And all you do is you mix things together for an hour and then rotovap things, removing everything and leaving behind just the acid chloride. Fairly, definitely very pure. So it's a really nice set of conditions. Okay, so the mechanism for this is quite awkward. Well, not awkward. It's fun. I like, this is my favorite, not because of the curly arrows. The curly arrows are always interesting, but just it's so practical to use. It's so reliable and you just evaporate. You don't have to purify things, which is great because purifying acid chlorides is really hard to do. As we'll see, they're just hyper reactive. Okay, so the mechanism for this is unusual. We're going to start with our catalyst. Okay, and that's going to be the DMF. Now, what I'm going to do with the catalyst is an acid chloride reaction. So that's why it's not, even though this is a fairly involved mechanism, it actually does introduce some interesting aspects of acid chlorides. So I'm going to first react that with the oxalyl chloride. Whoop. Okay, now the oxalochloride can be drawn as a resonance structure, and we're going to use this resonance structure for all of our acid chlorides. So I'm just going to consider one carbonyl with charge separation. Now, what we do with the DMF is we actually push the electrons on the nitrogen over to make a carbon-nitrogen double bond, and then the oxygen carbon double bond reaches over and attacks the oxalochloride. Now, you could attack from either of the resonance forms. You would have to push up the carbonyl electrons to get to a negative charge in the oxygen in the final product. But both of these are just different depictions of the same molecule. So adding DMF to either of them will give you the same outcome. Now, because of symmetry, we could add to either side, but turns out to just not matter. Okay, we're net neutral in the product where we have a positive charge on the nitrogen and a negative charge on the oxygen. Now, what acid chlorides like to do is they accept a nucleophile at the carbonyl carbon, then they take the negative charge in the next step, and they push the electrons down to remove a good leaving group. So in that case, we get the chlorine atom falling off. So it's generally the halogen that falls off. I'm going to swing down here. Now what the halogen is going to do, and then what we do is we get a net substitution of the chloride. If you look, the chloride's been replaced by the nitrogen oxygen. Now the chloride is going to swing back in. It's going to attack the carbon that's double bonded to nitrogen and push electrons into that nitrogen to neutralize the nitrogen and the overall structure. But that structure is not going to stick around too long. There are too many heteroatoms attached to one central carbon atom. The nitrogen is actually going to push its electrons over to make a carbon-nitrogen double bond. Then we're going to break this carbon-oxygen single bond, making a carbon-oxygen double bond here. Now we're going to break the carbon-carbon bond between the two carbonyls, pushing the electrons on the carbonyl carbon, and then pushing off the chlorine atom. That last half of the mechanism looks a lot like the oxalochloride portion of the making the active oxidant in the Swern reaction. Okay, so a lot of stuff is happening here. The ultimate outcome that we care about is we get this species. This species, which is bonded to, or not bonded, but countered by the Cl- atom, plus we actually form this molecule, which is CO2, plus this molecule, which is carbon monoxide. So we form CO2 and carbon monoxide. These evaporate away, and this drives the reaction forward. Okay, this is our reagent that makes acid chlorides. Okay. All right, I'm going to make sure that's zoomed out so you can see all the arrows. So it's this reagent that we form when we add the 1 drop of DMF. So our DMF, let's assume, is consumed and is now making this thing. Okay, so what we can do with this thing is we can recognize that the carbon-nitrogen double bond is actually highly electrophilic at carbon, where lone pair on the oxygen could add. I mean, there's a few ways that you could do this, but I think there's generally, under acidic conditions, let's see if we can add this without using the carboxylate. I may revise my thinking, but I'll be careful. All right, so I'm just going to spin this around so you can see how it adds, but I'm going to have Cl. It's just kind of a bummer to rotate things after I add. So we could add. This is what the species would look like if the carbon nitrogen bond was rotated around. We're going to add in both cases to the carbon nitrogen double bond and push electrons over to that nitrogen atom. That's going to give us this species. Okay, so this species is fairly unstable. Now what we can do is a few things. Maybe you want to lose the leaving group. So we're going to have nitrogen come and push this off. It's hard to know the exact order of events, but let's push off that nitrogen atom like we did last time. And shoot, I've got a positive charge here, don't I? Yes, I have a positive charge there. That's all I need. Okay. All right. Now, I don't like that. Shoot, I'm sorry. I don't like that double positive charge. My notes are getting messy. So let's just do this. Let's neutralize that positive charge right away. I think that makes the most sense. I'm sorry. Hopefully I did that fast enough to where people weren't writing things down so much. So we're under strongly acidic conditions, but this is a pretty strong acid. So let's just form some HCl here. I feel a lot better about this mechanism already. Okay. Now, the nitrogen can kick off the chlorine atom without making something that has two positive charges. Okay. Now, this is an interesting species. Cl minus from before that was countering everything, or the Cl minus that's released from HCl, whatever. We have a bunch of Cl minuses floating around, is going to add to the carbonyl oxygen and push the electrons up. So it's adding to that carbonyl oxygen. When it does so, it's going to have a negative charge at the carbonyl oxygen along with the rest of this positive charge here. Oh, and then the Cl minus, of course. Now, usually when the oxygen with the negative charge decides to come back down, it's going to reform a carbonyl. That's not a super weak pi bond. It's going to come down and reform the carbonyl and release a good leaving group. Now, typically that's chlorine, but in this case, it's actually going to be the rest of this upper part of the molecule, because we're going to take this carbon-oxygen double bond, or carbon-oxygen single bond, and move it over to make a carbon-oxygen double bond, move the electrons on the nitrogen over to make a carbon-nitrogen single bond with a lone pair. Now, the outcome is this. Now, what's cool about this is DMF. Okay. So we've regenerated the DMF. It's a catalyst for this reaction. Wait, those atoms, though, those aren't the same. It's not the same oxygen, right, that we added in originally to our DMF. Of course, it's a product and a starting material. It's a catalyst. You've heard me say that 1,000 times. Okay. Thanks for letting me show you this. It's one of my favorite reactions. I wanted to get the mechanism off my chest. Don't worry so much about having to predict this on a test or that sort of thing. But I at least want us to see how this is done. But this is just such a reliable reaction. So the complications come from the oxalochloride. But what this does do is this introduces us to how carboxylic acid derivatives react. And it turns out that acid chlorides are among the most reactive carboxylic acid derivatives. Okay. And it turns out we can actually kind of quantitate that a little bit. We could say, let's actually put the acid chloride all the way over here at the end of our page. That's going to be the most reactive. Sorry, most reactive. After that's going to be the next functional group we'll talk about in an upcoming lecture, but not today. That's the anhydride. I'll label that one. That one's a little unusual. Then we've got the ester. Okay, now over here in the middle is actually the carboxylic acid. So everything to the right of the carboxylic acid is more reactive than it. Now, less reactive than the carboxylic acid is actually another derivative, and that's the amide. And the least reactive carboxylic acid derivative of them all, it's kind of a bummer to call it a carboxylic acid derivative. It's not. I guess it's derived from it. It's fine. But anyway, it's just the carboxylate. So when you put a negative charge, you make this thing super, you really reduce how electrophilic it is. It's harder to put like a more permanent positive charge character at that carbonyl carbon when it's got a negative charge right next to it. So it's least electrophilic. Okay, so this is most reactive. This is least reactive. So we're increasing from most to least reactive, and this is the reactivity with a nucleophile, because that's typically how we see carboxylic acids and their derivatives react, is that they react with nucleophiles at the carbonyl carbon. Now we saw a hint of this in that mechanism to form the acid chloride, but let's look at more generally how these things react. So the general mode of reaction for a carboxylic acid derivative okay, and really carboxylic acids too, but usually you like protonate the carboxylic acid before you get them involved. But the general mode of reaction is called addition elimination. Now, put stars next to that, all capital, highlight it. I need a really big highlighter. There we go. Big time. Okay, addition elimination. Now, the reason why I want to literally highlight that is that this is it's a new type of substitution reaction. So we have a new type of substitution reaction on our hands. So in general, what you see is, let's just go ahead and just pick an acid chloride, because that's what we're going to start with today. We're going to see an acid chloride react with a nucleophile, and the outcome is going to be a carboxylic acid where the nucleophile has replaced the chlorine, and the chlorine is lost as a Cl minus. Now, the thing I need to highlight again here is, in this product, the substitution occurs at the carbonyl carbon. Substitution happens at the, I need to emphasize this, sp2 carbonyl carbon. Now, for reasons of molecular orbitals and that sort of thing, conversations I'm willing to have with us, with each of you, if you're interested, just let me know. But for the sake of making the material manageable, we're not going to worry about it here. But at sp2 atoms, we get no SN2 reaction. Okay, SN2, that big substitution reaction where the nucleophile attacked the carbon, pushed off the leaving group, and substitution occurred. We don't get that at sp2 hybridized carbon atoms. If we don't get that, that means we don't get all the other things that come along with it, like efficient reactions, concerted mechanisms with no intermediates, inversion of configuration with controlled stereochemistry. None of that is relevant here. It's a substitution. That's what we're doing. That's what's similar, but it's not an SN2 reaction, because there's no SN2 reactions at sp2 electrophilic atoms. Instead, we do addition elimination. Now, here's what addition elimination looks like. We've done this a few times already. We just haven't called it addition elimination. And this is a really important mechanism and a really important few minutes of lecture content, because this is the mechanism we're going to do over and over and over again until the end of this little module, this little unit in the class, which might be the end of the class. So the way this works is we're going to take our carboxylic acid derivative. So I'm just going to have some generic X group here. If you want to think about it as a chlorine, go ahead. We're going to consider, we could consider a resonance structure. I'll do that in a second. What we're going to do is add the nucleophile. It's helpful if we get comfortable recognizing that nucleophiles can add to carbonyl carbons and push electrons up. That's a really helpful thing to consider. But alternatively, if you need to look at the resonance structure, I would never argue against drawing more resonance structures. We could add there if you need to and just forget that second arrow. When we do this first step, this is our addition. The nucleophile is adding to the carbonyl carbon, at which point we form what's called the tetrahedral intermediate. I just made a big stink about how the tetrahedral about how we need a tetrahedral carbon and sp3 carbon to do SN2 reactions. So this intermediate is involved halfway through the addition elimination reaction, and it's important to point out when we have this tetrahedral intermediate. The reason why it's called tetrahedral, the tetrahedral intermediate, is because our carbonyl carbon is now sp3, and if it's sp3, it's tetrahedral. Okay, so we must add to form a tetrahedral intermediate, and then we eliminate. The elimination occurs when the negative charge recognizes that it can come back down to reform the carbon-oxygen double bond and kick out the best leaving group. The best leaving group is probably not the nucleophile. Okay, that would just give back the starting materials. It's typically that thing that makes or defines the carboxylic acid. And so we lose the leaving group as a negatively charged species and we get the nucleophile. I'm going to go through this mechanism over and over again in the various contexts of all the different reactions that we're going to study. I'm going to try to say things like, here's the addition, here's the tetrahedral intermediate, and here's the elimination. Sometimes we have to do some special stuff, like if you look at the Fischer esterification, we protonate the carboxylic acid first, then we add, the intermediate is tetrahedral, we eliminate, we still need to lose that proton to regenerate the carboxylic, or to regenerate the acid catalyst, but then we're back at our product. So there's kind of two steps outside of the addition elimination. If you know this mechanism and you're comfortable with this mechanism, the next step is to just be able to recognize the carboxylic acids, have some idea of their order of reactivity, which I showed up here. And then you've got really all the mechanisms for the entire unit, right? So that's kind of exciting. Okay. So no SN2, but we add, we form an intermediate. So this is not a concerted process. And then we eliminate the best leaving group, which is typically that thing that defined the carboxylic acid. Okay, so we can actually use this reaction with acid chlorides to make all sorts of derivatives. Okay, so acid chlorides are great starting materials for all sorts of derivatives. Okay, so for example, you can take an acid chloride, all right, and let's treat it with H2O. And if we do that, we get the carboxylic acid. Okay, so what happened here? Well, let's recognize that in many cases, we also form HCl as a byproduct if the acid chlorides are starting material. So here our nuke is the OH that's on H2O. So typically to get this reaction to work, we have to add some sort of base. And that's going to be true for most of these acid chloride reactions. We have some base present because the base either deals with the HCl that's generated or it allows us to make our nucleophile a better nucleophile. Now, water reacts fairly efficiently with acid chlorides. It's really helpful if you have some base. You can actually do some interesting things without base and get acid chlorides to hang around a little bit, which is fun. Okay, so making carboxylic acids can be a thing from acid chlorides. Now, you typically have made the acid chloride from the carboxylic acid, so it's hard to find opportunities where that makes a lot of sense strategically. But you can replace the H2O with an alcohol and do the exact same reaction to form an ester. So again, we're going to have some sort of base present, and that's going to give us a carboxylic acid derivative where the R group is now attached to the O, and so this becomes an ester. And all we had to do is replace water with alcohol. Okay, we could kind of keep going here, but we've hit carboxylic acids, we've hit esters. We could, don't mean to do that. We could even take this and react it with a carboxylic acid. I'm going to put an R group over here with some base present. And that's going to make an anhydride. So here in this case, the nucleophile where all of those atoms minus the acidic hydrogen, which is either sopped up by the base or makes HCl, which we have to deal with later. But this then gets this weird looking product, the anhydride. And then lastly, we can take acid chlorides and react them with amines. Now, if you take an acid chloride, react it with an amine in the presence of some base, you're going to get an amide or amide, depending on where you're at. So we now have access, if we think about it, let's see, what carboxylic acid can't we get access with directly from an acid chloride, ignoring like other acid halides or something like that? Well, we can get, it looks like we can get all of them, right? Except for the carboxylate. Well, the carboxylate just comes with more base. I mean, we have to start with the fundamental properties of carboxylic acids, but in terms of a starting point to see all of the reactions and all of the access to the other reagents, acid chlorides are the one to start with, okay? They smell kind of funky, but generally, and they are a lacrimotor, it turns out, which means they can cause your sinuses, I'm getting teary-eyed thinking about it, your sinuses to kind of swell up a little bit. I just remember my first summer as a research intern, and I was such an idiot. I was like wipe my face with my gloves. It's just so stupid. But I did a ton of stuff with acid chlorides because they're super useful. This is one of my favorite units in all of Organic 1 and 2 because everything we talk about are like reactions people do all the time, whether it's in organic chemistry or biochemistry. So these are chemicals that are handled quite a bit. So I was doing the reaction, all the chemistry was working great, but like I didn't know why at 4 o'clock I was so tired. And it was because I wasn't tired, but my eyes were like swollen a little bit because I'd rubbed them with the residual like acid chloride on my gloves, which isn't great for a lot of reasons. And obviously safety's improved a lot since then. But yeah, so that was a bummer because then it would be like summer research internship, and at 5 o'clock I'd be like, oh man, I think I have to go to bed or something. You know, all I needed to do was take a shower and wash my face, and I would have been good. But anyway, you know, don't touch your face with your gloves. I guess that's the lesson for the end of the lecture. Okay, we'll pick up with more acid chloride chemistry in the next lecture. So we'll see you then.